Welcome to Chapter 4, Basic Probability. This is a chapter that you should be quite familiar with as you use these kind of probability statistics or calculations a lot in your life without even realizing that you do it. So what are the basic probabilities? You have two. One is the probability to succeed and one is the probability to fail. They're inverses or reciprocals of each other. So if the probability of success is 60%, the probability of failure is 40%. And we're also going to talk about some basic concepts uh, and conditional probability, which I'll get to in a moment. They help us get a distribution rather than just a specific number. You have a range of numbers. And a couple that we'll deal with are binomial and Poisson. And eventually we'll get to what's called the normal distribution. So you have 6 sides of a die. I'm sure that most, if not all of you, have rolled dice at some point in your life, and you know the probability of getting from 1 to 6. They're all equal. So 1/6 of getting a 1, 1/6 of getting a 2, etc. When you combine them, though, when you have 2 dice, there's no way to get a 1 because the smallest is a 1 and the smallest is a 1, which would be 2. And the highest number is a 12. And you get a probability distribution that would be, you all know that rolling a pair of 1s is less than rolling a 7 because there's no more ways to get a 7 than there is or a 2. I might have said a 1, sorry about that. And also getting a 12. The only way to get a 12 is to get a pair of 6s. The only way to get a 2 is a pair of 1s. Well, there's, a 4, you could get a 2 and a 2, or a 3 and a 1, or a 1 and a 3. And then, of course, if anybody is a fan of poker, they know all about probabilities. If you've ever watched poker on TV and they talk about the probabilities, they're on the screen of drawing certain cards or winning certain hands. So you have simple events. It's only one characteristic. A day in January from all the days. So there's 31 days in January. Pick any number you want from January. There's 1/31st or 1 in 31 chance. Joint event, okay? In this case, it's got more conditions to it. It's a day in January, but it's also a Wednesday. So there's, depending on the year, there's either 4 or 5 Wednesdays in the month of January. And a complement would be the reciprocal or the inverse of that. So all the days from 2020 that are not in January. So considering it's a normal year, 365 minus 31 would be 334 days that are not in January. So it's the opposite. Probability is always between 0 and 1. 0 means there's no chance of it occurring, or it's impossible. And a 1 means it's certain. And very few things in life have certainty. Some of you probably have heard the joke, death and taxes are the only 2 certainties in life. It's intended as a joke. It's a bad joke, all right? So in this particular case, mutually exclusive simply means you're trying to pick a day that occurs in January and also occurs in February. Well, that's impossible. It's 0. You have to pick a day from January or a day from February. So the word or is important. So A and B are, there's no way for it to be in both months. So in this particular case, you can have days that are weekdays and weekends, so they're mutually exclusive. You can have a day that's in January or a day that's in the spring, and at least in North America, January is not part of the spring. It's definitely part of the winter. But you can't have a day that's a weekday and a weekend. You can have a weekday or a weekend. You can have January or spring, but you can have a weekday in January. You can have a weekday in the spring, etc. So just follow more your logic. When I've taught this in the past, some people start getting all hung up on the formulas. Just follow the logic. I want you to pick a weekday from January. Is that possible? Yes. I want to pick a weekend from the spring. Is that possible? Yes. I want to pick a day of the week that is both a weekday and a weekend, and that is not possible. So in this particular case, you take the probability, the number of days in January, just so happens that 2020 is a leap year, so there's 366 days. And so you simply take the probability the day will be from January when it's randomly selected in 2020, be 31 over 365. So you have a table here. You have people taking statistics, not taking statistics, and they're broken down by male and female. And so you can see you have 4 different combinations between male, female, taking stats, not taking stats. Probability that of a male taking stats. So in this particular case, they have to be both male and taking stats. There's 84 that are male students taking stats out of 439. So about 19%, 0.191 to be exact. Now, again, you have a probability table, and this is a 2x2. Yes, no, yes, no. I plan to purchase a TV and actually purchase a TV. So you can see the total sample is 1,000. So you can, somebody who planned to buy the TV was 200, and they actually did buy it, but they planned to buy a TV, and then something came up and they didn't, was 50. So in this particular case, you also had some people who said, no, I don't plan, 750 people said, I don't plan to buy a TV, but out of that group, 100 did. Now, maybe there was a really good sale on, or they got some extra money, or maybe their old TV just gave up the ghost to say, just stop working. So then, again, don't tend to worry so much about the formulas, just follow the logic. So in this particular case, actually purchase the TV. Out of 1,000 people, 300 purchased TVs. So that's where you get, sorry, 250 purchased the TV, or sorry, said yes, but that represents 250 out of 1,000. But it actually turned out that more people than you had thought, because remember, 250 said they were going to buy a TV, 50 of them dropped out, but out of the 750 who said they weren't, 100 newcomers came along. So 300 out of 1,000 people actually bought a TV. So that's from the yes column divided by the total. And I've already mentioned this, 200 said they were going to buy a TV and did. So companies would know this. For example, at the schools, you will get students who say they're going to go to your particular school. Fine. Some of them don't show up. That percentage is actually about 20% from what I've been told. So if 1,000 students say that they're going to show up for classes on the first day, only about 800 of them actually go, at least from what I've heard in the past. Now, if you have 1,000 spots, you actually need to say 1,250 acceptances. All the schools that I teach at accept more students than they have spots, because they know that they have a certain percentage, although they fully intend to go, they don't. When I was your age, I twice applied to go to the University of Manitoba. I never went either time. I wound up going to the University of Saskatchewan instead. So, and it's nothing wrong with it. It's just people change their mind if something comes up. Maybe something comes up where they can't afford to go, or maybe they decided to wait, or they found another program, or they've been accepted at another school. So in this particular case, the planned, which is yes and yes, is 200 out of 1,000. And then there was, they planned to, but they didn't, was 50 out of 1,000. So there was 250 out of 1,000. You simply take the total column. So 25% of people surveyed out of 1,000 intended to buy a TV. 200 of them actually did. So 80%, 200 divided by 250, actually said they were going to buy a TV and did. So that would be equivalent to what the analogy or that I just used, where you said you were going to go to school and you actually did. So it's about 20% from what I've been told. So again, there's different possibilities here. So the planned and the actual purchased would be 250 plus 300, or all right. So minus the 200, and you get 350 that they planned and purchased. So you can see where they get the numbers on it. So you take the 250 from the yes, yes, you add the total, and then you subtract the, so you take the total from the yes row, the total from the yes column, and then subtract the intersection point to make that more clear. It said planned or purchased. So you take the percentage who planned, that would be the yes row, yes column, but you're double counting the 200. Does that make sense? So let me say this one more time. The planned, 250 people planned to buy a TV. Got that. 300 actually purchased a TV. Got it. But there are some people in there who you are double counting. It's like this example. You have a group of students and you count the number of students in class who have blonde hair. Fine. And so then you also count, and then of course you have the number of students who don't have blonde hair. Then you count the number of students who have blue eyes. And there will be then the students who don't have blue eyes. Now, you're double counting the people who are blonde haired and blue eyed. So if you have 1, 3, 5 in a class of 30 or whatever that have blonde hair and blue eyes, you're counting them twice. So you have to take that out, the people who have both characteristics, because it says or. If it said and, then that would only be the students who have both characteristics. All right. So a conditional probability in this particular case, as this is actually something I mentioned earlier. What percentage of people who planned to buy a TV actually did? That's what this answers. So 200 people out of 250. 250 said they were going to buy a TV. 200 carried forward with that. So when companies do surveys like on the internet and things like that, they say, do you plan to buy a car in the next 30 days or 90 days? They understand that a certain percentage of those people, they might fully intend to, but something comes up where they change their mind. They're going to wait till next year's model comes out, or they get laid off of work, or whatever the case may be. So out of the 250 who said yes, only 200 of them carried forward. Here's a decision tree, which just represents the table in different ways. So planned, 250, 200 actually purchased, 50 said no. Under the did not plan, or weren't going to buy a TV, remember, it's not part of the plan. So in this particular case, you had 750, 100 actually did change their mind, and 650 said, no, I'm not planning to buy a TV, and guess what? They didn't. So there are the different combinations that you have. It's just represented in a decision tree. So as I said earlier in our little presentation, the percentage of people who plan to buy the TV and actually purchased it was 80%. So the percentage of people who didn't purchase a TV, the no column, was 70%. And that also tests for independence. If the two numbers are the same, the 80% and the 70, that means they are, okay? So the two probabilities are not equal. So these two events are dependent. If they're the same, they're independent. So if it's 80-80 or 70-70, then they're independent. So so you just check the probability of each, and if they're the same number, they're independent. If they're not the same number, they're dependent. So we dealt with some basic probability concepts, and we also dealt with conditional probability.